Yeah, so welcome back to the last hour for today. And so the last question that we would like to discuss now with this inviscid instability is the question of, you know, why is it so that there's a viscous instability? Let me stop also this transcript. So why is there an inviscid instability? Why is there a viscous instability for cases like Poiseuille and Blasius, whereas typically we would expect that this is not happening because viscosity would actually be stabilizing? Well, in this case, apparently it is like that viscosity makes the profiles unstable, which is again not what we would consider or what we would expect, but this is what happens. So that means that TS waves are in fact a viscous instability, which is quite interesting. Well, if we now think of a physical explanation of why this happens, or why this can happen, is, well, let's consider again our good old friend, which is the Reynolds-Bohr equation, which of course is a viscous equation. I just write it down again. It was the change of energy in a domain, and it was written like this: the dE dt is the integral of uv times du dy dy minus 1 over Reynolds of the integral. Now write it with omega, with the vorticity, but that doesn't matter. So the vorticity squared. And this is an integral over, well, it could be the domain or it could be just the vertical profile. Well, and we identified this term and this term to be the production of fluctuations, and this one would be the dissipation. So again, we always consider here the departure from the mean flow. In this case, it's non-linear, or actually it's linear as well. It doesn't matter because the transport terms have fallen out. But it's always the departure from the base flow that we look at. So we have the production and the dissipation term, and if we now try to plot the relative size of these terms as a function of Reynolds, we have dE dt here. Well, what we know is that the production, so if you start with the production is actually 0 for low Reynolds numbers. This is what we talked earlier. So it kind of goes up at some point, and then we also know that the production is actually 0 for high Reynolds numbers. So it would probably look like this. This would be the production as a function of Reynolds. The dissipation, on the other hand, is very large for low Reynolds numbers because you have the 1 over Reynolds here. And it would probably look like that. It would also go to 0 if the Reynolds number is infinity, because then the whole term would disappear. So this is the dissipation. Now, what we know from earlier, there's this crossover point, and this is what we said is the, you know, this Reynolds G, where for the first time we have growth through linear effects. But the important thing is at Reynolds infinity, we have the production and the dissipation 0. Now, you can ask yourself, okay, so why is the production actually 0? Well, so the reason why the production is 0, if I write it like this, it means, or it is due because U and V in the absence of viscosity, U and V are uncorrelated with each other, because there's no viscosity that kind of makes them to move in a specific way. So they're just uncorrelated, and that means that the UV product, so the correlation between U and V, is actually 0. And what happens for lower Reynolds numbers is that the viscosity induces a phase shift, a specific phase shift between U and V, and that makes then the correlation of U and V to be non-zero. So for the production, it means that the viscosity creates a phase shift between U and V, and that makes then the correlation U times V to be, well, not necessarily like this, but not equaling 0. Okay, now, so we know it goes to 0 here at infinity. We have this crossover point, but then we have this whole region now, the shaded or the hatched region here. This is the region where we actually have production larger than dissipation. And of course, that means at the end of the day, because the dE dt is the difference between the production and dissipation, this means that dE dt is larger than 0. So it goes again to 0 at infinity, it's 0 at rate g, but in the whole region in between, there would be too much production as compared to dissipation. And I guess in the end, we can say that we can see from this consideration that it's really the viscosity, the act of viscosity, making the production to be non-zero that creates this this instability for TS waves. So it's really this balance between production and dissipation that is relevant. Okay, so this is to kind of motivate why TS waves really are a viscous instability. And the last thing I would like to do here, before we then go to the last topic, I would just like to go back very quickly to, so now we have talked about Poiseuille and Blasius, but I would like to spend maybe 5 minutes on the Kelvin-Helmholtz instability. So the second example would be the Kelvin-Helmholtz instability as one prime example of an inviscid instability that we see everywhere, as we have talked before. And I will upload on the homepage a derivation of how you can actually do it formally. What I would like to do here in the lecture is just a phenomenological study of motivating what type of instability actually happens in the Kelvin-Helmholtz instability and how we can explain it on a very simple, very straightforward mechanistic way. But of course, it's very consistent with our derivations that we did with the Rayleigh inflection point theorem. So, okay, so the Kelvin-Helmholtz instability goes back to William Thomson, who later became Lord Kelvin, and he lived 1824 to 1907. And then we have the other famous scientist here. It's Hermann Helmholtz, who lived 1821 to 1894. So the idea is that you have the flow case, or the archetype for a Kelvin-Helmholtz instability is like this, that you have two streams, that's too much. the two streams of velocity, one like this, and then the other one a little bit faster. So something like this, and then you have here a little bit lower velocities. You would then define a coordinate system, which maybe looks like this. This is x, and this would be y. And well, in the end, you would then have kind of this separation between the high velocity, which we call u1, and the low velocity, which we call u2. So it's really the case where we have two different streamwise velocities, where u1 is larger than u2. And as I said, we can derive that analytically, and we can actually come up with a quite nice result at the very end. I will say that, I mean, this is in the lecture notes or on the homepage. So we have all the derivation, but here I just would like to show you the main result. We actually get an instability based on the Rayleigh equations. We get an instability with a complex phase speed, c being 1/2 of u1 plus u2 plus minus I divided by 2 of u1 minus u2. I mean, remember again, it needs to be complex conjugates because the Rayleigh equation is fully real. So this is the solution for the complex phase velocity. And of course, that's quite interesting because it turns out that this guy, 1/2 of u1 plus u2, we can say this is just the mean velocity between the two streams. It's just the average. And this guy would be I times delta u, which is the difference between the two velocities. So we have the mean and the difference. So that means that the complex phase velocity that we will get is just u mean plus minus I times delta u divided by 2. Actually, it's like this. Now, what about the growth rates? Because now from this wave speed, complex wave speed, we see that the real part is just u mean. So that means that the wave is essentially traveling with the speed of the average of the two streams. And then the growth rate, so that's the complex or the imaginary part, that actually is proportional to the velocity difference. So if you just want to now get the growth in time, which is maybe the easier way of looking at, so we just calculate the complex growth rate, which is then the complex omega, which is just alpha times c, which then becomes alpha times u mean plus minus I alpha delta u divided by 2. So that means that the actual growth rate in time is this guy here. That's the complex, so that's omega I, if you want. So growth rate is thus omega I being alpha times delta u divided by 2. And of course, that's quite interesting because it first of all tells us any wave that you have with any alpha is growing in space, is growing in time. So any alpha is growing and it's proportional, the growth rate is proportional to delta u divided by 2. So the larger the velocity difference is, so the larger the shear is, the more you grow. So that's one result. So all waves grow and it's proportional to the velocity difference delta u. When I say all waves grow, that's true, but the growth rate is still proportional to alpha. So that means that the short waves grow fastest. So the shorter the wave is, it would grow faster because it's proportional to alpha. And of course, that also shows you a little bit the limitation of this inviscid analysis, because now it's clear also that short waves would also have the largest dissipation. So that means in the actual viscous case, when you have a finite Reynolds number, you would actually see that smallest waves would probably not grow, and you would have somewhere a maximum, and that is the maximum of growth that you would then also see in an experiment. But the important aspect here is that very long waves would perhaps not grow as much. So where you have low wave numbers, the growth rate would be quite low. Okay, but I promised you also a physical explanation of what actually happens, because so far this was just a mathematical analysis based on the Rayleigh equation, but there's actually quite an interesting mechanistic explanation of why you would actually get such a strong growth in for a mixing layer, or for this stream with two different velocities. Well, so the argument goes like this. So let's assume that we have now a wave. You know, that this interface is not straight anymore, but it's already a little bit bent. And of course, that could be an infinitesimal bend, which is then just starting to grow. Okay, so what may happen? So let's first look at this part here when we have a deflection to the downside. If we assume that somewhere we will have a wall, somewhere in some distance, and then you have this interface deflecting downwards. Well, what would that happen? What would that mean if you look at the lower side? Well, because suddenly the flow has only a shorter or a lower area to flow through, it would actually mean that we get an acceleration in this region. So the flow gets faster and faster. What does acceleration mean when you think of Bernoulli? Well, we actually have the pressure going down. In this case, again, if you look at the lower wall, we have exactly the opposite. We have a deceleration, and that means that the pressure goes up. And if you now go to the other side, so here and here, well, obviously we have exactly the opposite situation. Here we have a deceleration, meaning that the pressure goes up, and here we have the pressure going down because it's an acceleration. I guess now you start to see kind of the argument. Well, if we have the pressure going down here and on the upper side going up, well, that means that we will have a resulting force, which is actually going in this direction. Higher pressure on the top, lower pressure at the bottom. In this case, it is actually the opposite. So we have a pressure force, a resulting pressure force that goes upwards. So that means, now with a very simple mechanistic explanation, but it's also inviscid, which is important here. So it's kind of connected to the Rayleigh theorem. It directly shows that if we have an infinitesimal wiggle, it will just continue to grow, exponentially grow, because we have this resulting pressure force, which is exactly in the same direction as the original deflection was. And of course, that's exactly the type of instability that the Rayleigh equation, or the Rayleigh equation was picking up. So we can now say that we actually have found a kind of Bernoulli type of explanation, mechanistic explanation for the growth of instabilities in this case. So that means whatever infinitesimal noise we have, it will just start to grow. Okay, so with this, I would like to stop with the inviscid instabilities, so the Rayleigh criterion, and actually move to my last topic, which will keep us busy now for today, and then, as I said, maybe an hour or so in a week. And this last topic, well, actually, first I would like to ask whether there's any question regarding the inviscid cases.
Yeah. Could you repeat why short waves grow faster?
Why this is the case?
Yeah.
Yeah.
Yes.
Well, essentially, it's if you look at the growth rate. So, I mean, if you believe the result that I wrote here, namely that C looks like this, which is, as I said, I will upload the derivation of that, which you can look at if you're interested. So this is the growth rate in, well, that's a complex phase velocity, I should say. If I would like then to calculate the growth rate in time, so imagine that I'm at a specific point and I just see how the wave is growing in time. Then, of course, I just take the imaginary part of omega, which is essentially this guy here. So alpha times delta u divided by 2. And of course, if I just look at the imaginary part, it's alpha times delta u divided by 2. And the fact that there's an alpha in there says that the growth rate as a function of alpha is proportional to alpha. So that means higher alpha, meaning short waves, they have a proportionally larger growth rate. So that's the explanation here. So in the end, you will have an e to the I omega t, and then of course the growth rate would then be the imaginary part, which then becomes an exponential growth. Okay?
Yeah, okay, perfect. Thanks.
Thank you. Okay, so good. Then let's go to the last topic of this course, which is actually, well, I'm not sure it's the most interesting one, but it's the most disturbing one, because it kind of puts a lot of question marks of some of the relevance of things that we talked about, but only at first sight, because then in the second part, you will also realize why it's still very important. But what do I want to talk about? I would like to talk about subcritical transition and non-modal growth. So this is the last topic. Well, it's essentially related to the typical diagram that we now drew many times. So we have the Reynolds number here, we have Rho C, and we have Rho G. And just for completeness, well, this is again when I have dE dt is lower than 0, below Rho G. Then here we have unstable eigenvalues, that's above Rho C. And our big question now is, so if these are the demarcation lines, our big question is, what happens actually in this region? Well, maybe first it's kind of interesting to think of what are actually the numbers for Rho G and Rho C. So how big is this region really? Well, if we now go kind of back historically, how things developed. So the first time people were applying stability, or the Orr-Sommerfeld equations were derived 1908, 1910, somewhere there. So the viscous equations, so where the Reynolds number actually matters, because I may also want to add here one point for Reynolds being infinity, that is the Rayleigh equation. But the viscous equations were for the first time applied or derived 1910 or so. And then, of course, people started to trying to find solutions to those equations. It actually turned out that that Rayleigh, which we know from before, has actually applied that to the flow between two plates with different temperatures. And that, of course, is something that is nowadays known as the Rayleigh-Benard convection. So the flow case is like this. We have two plates, and the upper wall is cold, the lower wall is hot. So that means that there's a buoyancy force. And then what you see is for specific values of the Rayleigh number, not the Reynolds number, but the Rayleigh number, which is the same as the Reynolds number, but for these forced convection cases, you get this kind of waves where you have an upward and a downward and an upward motion with a specific wavelength and a certain growth rate. And as I said, this case was essentially driven or is driven by the Rayleigh number. And it turned out that the stability calculation showed that the critical Rayleigh number is 1,708. Now that's a value that you can calculate. It's maybe one page of derivation. We do that in some of our basic fluid mechanics courses, where you can derive that. So it's not a big, it's not very difficult. It's essentially just using your Sommerfeld equations. Now, if you went in an experiment and you tried that, so you had your experimental setup. These days we can also just do a simulation. You can actually reproduce this value extremely accurately. And I have here a slide where I can show you that, just to convince you. So this is the stability diagram, the banana curve for Rayleigh-Benard convection, where you see this critical point here, which is at this 1708, and here it actually turns out that this is approximately pi in terms of the wavelength. So, and if you now do simulations of that, as a you can consider a simulation as being a numerical experiment, you can actually see that for the case of Rayleigh being 1,700, so a little bit below stability, the stability limit, nothing happens. You just have laminar flow. But as soon as you're a little bit above, so 1715 in this case, you start to see kind of this wavy motion. And of course, this wavy motion becomes stronger and stronger the higher you go in Rayleigh number. But the important thing is that there is essentially, so the critical Rayleigh number is really the demarcation between stability and instability. So that means in this case, it actually turned out that you went directly from kind of the case where you have no energy growth to growing eigenvalues. So that meant in this case, it turned out that Rg is the same as Ra, the Rayleigh number, sorry. It's the same as the critical Rayleigh number. And of course, at the time, people didn't really know about the difference between Rg and Rc. And this was really celebrated as the success of linear stability theory. But then later on, people were also trying to do channel flows and boundary layer flows. And as we discussed last time, the first solutions then for boundary layers were found by Tolmin and Schlichting, with the TS waves. But in channel flows, it then turned out that the critical Reynolds number is this 5,772, which we got from your Sommerfeld equations. But actually, and that's the sad thing, is that Rg in a channel is 49.6, so much, much, much lower. Essentially, you will get that by doing this very similar analysis for the Orr-Sommerfeld modes, but you do that you do that in the context of the Reynolds-Orr equation. So you have this gap between 49, where you know that nothing grows, up to around 6,000 when you have unstable eigenvalues. So this region here, the blue region, the question mark, is actually very, very big. And experiments have shown that there is actually transition, or I mean, there is instabilities growing even for Reynolds numbers below Rc. So essentially it means that there is an instability despite all stable eigenvalues. And what we also know, this is not some kind of strange nonlinear stuff. It is actually a linear process that needs to happen here, because it's actually based on the Reynolds-Orr equation. Because we have shown with the Reynolds-Orr equation that there is actually energy growth in this regime. But it needs to be a linear process that is happening. So that means in this region, what actually happens is what we call subcritical growth. Of course, this doesn't mean much, because subcritical just means that we're below the critical Reynolds number. But somehow we still have growth based on linear principles or linear mechanisms. So that means it should be possible somehow of finding quite simple equations, linear equations, that determine how this, or at least give us the reason for this growth. And this is actually, so what will come out here is something that is called transient growth, or also non-modal stability. Transient growth, we will see later on why it's called transient, because it essentially means that this growth cannot continue forever, because all the eigenvalues are low, are stable, so it can only be transiently growing. And non-modal stability means it's not individual modes that grow, because as we know, these are stable, so it's actually non-modal growth. So it's not individual modes, it's a combination of modes that may actually grow. This is a fairly new concept in fluid mechanics. So from the 90s, maybe of the last century. Well, that means in the meantime, it's already 30 years ago, but still it's a fairly modern approach. Now, for this, I would also like to just show you one example, which kind of determines the relevance of it. So if we now look back to this case here, which we call, well, classical transition, classical in that sense, meaning that it's the modal growth of TS waves. And then remember, we had these TS waves here, these span-wise sausages, which then slowly grow exponentially up to the point that they actually become non-linearly saturated. They start to wiggle in the span-wise direction, then give rise to these, what we call hairpin vortices. So this is the classical picture, and this happens at supercritical Reynolds numbers. But now the situation that we're having now is a little bit different, because we have transition actually at Reynolds numbers that are lower, where the flow is in principle stable. And at in the very early days, this was called bypass transition, because it bypasses the exponential growth of instability. Now bypass transition has become kind of synonymous to the transition scenario that is induced by non-modal growth. And one example where this happens a lot is when you have a flow which has a lot of free stream turbulence, which then penetrates into the boundary layer. It creates these streamwise streaks. That's exactly the ones that then grow transiently, but these streaks then become unstable and lead to the breakdown to turbulent spots. So bypass transition is happening in those situations when this exponential growth, so everything above Rho C, is bypassed, is not the relevant transition scenario anymore. And this happens, for instance, in turbo machinery, where you have a lot of free stream turbulence, where transition is much earlier, as if you would expect it from just the growth from TS waves. And of course, that's exactly the reason why we had this issue in the E to the N method, where we had to reduce the critical N factor by something proportional to the turbulence intensity, because the experiments showed that as soon as you have enough turbulence intensity, your N factor actually goes down. Okay, so how does this look like in a video? Well, it's kind of something like this. You have free stream turbulence coming in here. You have these transiently growing streaks in the boundary layer, and then you have these turbulent spots, growing every once in a while, and they kind of come out of nothing, and they lead then to turbulence. So this is a completely different transition scenario as compared to the classical scenario. So, but now the question would be, if we come back to the theory, the question is, how can we actually understand this? So what is happening on a mathematical level? Well, I guess for that, we again need to kind of go back a little bit, or back up a little bit, and look at our original problem that we studied for stability. So the dynamical system that we looked at was something like that. dq dt is L times Q. And in a discrete setting, Q would be a vector and L would be a matrix. So what we looked at so far was we did normal modes. So we looked at normal modes here. So we said that the Q here is some sort of Q hat times e to the I alpha x minus omega t. So that's the way that we considered everything. And what we were mainly interested in was this eigenvalue omega, which has the, if you plot it in a spectrum where you have omega r and omega I, you had then a few points in the spectrum, and then we had these guys here that were that had an omega I which was larger than 0, and this would indicate growth if the Reynolds number is larger than Reynolds C. But now we have seen that sometimes there is growth even below, and that's what we would like to understand. Well, how can we do that? How can we, or what is missing in this consideration? Now, because we only have 5 minutes today, I would just like to show you the basic idea. So far we have looked at the growing eigenvalues, but right now we would really like to do something that is called an input-output analysis, in the sense of the following, that we write everything right as a matrix exponential. Well, what does that mean? So we would like to look for the solution of the differential equation that we have written above. So this dq dt being L times Q. Well, how can we write that? Well, we know the solution if this was scalars, which was just Q being the exponential of t times L times Q0. So this works fine if we were to look at scalars. That's just the solution of this equation. But now we can just write that as well, even though Q and Q0 and L are vectors and matrices, respectively. And this is now what we call an input-output formulation. In the sense that the Q here would be the output, and the Q0 would be the input, and this guy here in the middle would be kind of a transfer function. So we take our input, which is Q0, we have the transfer function, which is this e to the t times L, and then we have an output for a specific time t. And that's just a solution of our linearized equation. Now, the only difficulty here is that this thing here in the middle, that's not a it's not a standard mathematical operation, but this is a matrix exponential. And the matrix exponential has a nice definition, namely that well, we could write it like that e to the x is nothing else than an infinite sum from k being 0 to infinity of 1 over k factorial times x to the k. So this is the matrix. That's the definition of the matrix exponential. And of course, if you would feed in instead of a matrix x, you would just fill in a scalar value. So x being a number, then this would just be the Taylor expansion of the exponential. So it's nothing else than the extension of scalar values to matrices. And in fact, the e to the x, so a matrix exponential, this is a valid operation. And for instance, in MATLAB, you find that operation. So instead of writing x, it would just be xm as an operation. And then you would evaluate the matrix exponential. Okay, so why can this be actually useful? Well, what we are interested in today, because we're talking about growth, is the following question. What is the maximum energy that I can obtain at a time t? Because you see there's a t inside here. So what I'm interested in is kind of in this input-output setting, what is the maximum amplification that I can get for a specific input to get an output? So what we would like to know is this g of t, which we can call the energy amplification. And we would like to have this as the maximum of a norm of our q at a time t divided by the energy of our initial state q0. So we would like to have, we would go from q0 to q0, and we would like to maximize the growth. So to get the highest energy for a unit energy in the beginning. And of course, we need to maximize this over all different q0s. And now it turns out, if this g of t is larger than 1, then it means that we have energy growth. And if this G of t is lower than 0, lower than 1, of course we don't have growth. But as soon as we have growth larger than 1, it means there's some mechanism in there that allows me to have increasing energy in the system. So it's essentially trying to find the best Q0 that gives me the most growth at the end, and then also trying to understand why this actually happens. This is all about, or this is at the heart of this transient growth or non-modal stability analysis. And as I said, there is maybe, it's actually not much, it's really two or three pages more that we need to look at next time to fully understand at least the basic idea behind this growth. So therefore, I would like to continue this on. Now let me just be sure about when it is. I think it's on Friday the 19th in the afternoon, where we would conclude this, maybe an hour and a half. And of course, I'm also very happy at that point to answer any questions you may have. But then I guess for today we can close. I stopped the recording.